Welcome everybody to Algebra 1, Section 4.1. Today we're going to talk about relations, functions, the difference between the twos, domain and range as well. So the coordinate plane, let's start here. So a coordinate plane is a plane, not like an airplane, but it's called a plane, just a region that is formed by the x-axis and y-axis. And so parts of this coordinate plane, so we have the origin, quadrants, x-axis, and y-axis we'll talk about here. So the x-axis runs horizontally left to right, where the y-axis runs vertically up and down. And for the x-axis, as you go to the left, those are negative values, and the right are positive values, similar to a number line. And in the middle here would be 0 for the x value. And then the y-axis, as you go lower, it's negative, and as you go higher, it's positive, with once again this middle here being a y value of 0. And the middle here being a y value and x value of 0 makes this the origin. So this is what we call the origin. And that is the ordered pair 0, 0. We'll talk about ordered pairs in just a moment. And then we also have quadrants. So starting in the top right, we have this quadrant 1. And then going counterclockwise around the circle, we have quadrant 2, quadrant 3, and quadrant 4. And as you may notice here, they're all represented by Roman numerals. Once again, you start with the top right and work your way counterclockwise to identify the 4 quadrants. Now let's talk about an ordered pair. So an ordered pair is a point on a graph. Now, the ordered pair is written as x, y. It's alphabetical, x coming before y in the alphabet. And the x is once again talking about how far left and right it is. The y value is talking about how high up and down you are. So for example, here we have these 6 points A through F plotted on this graph to the left. And we're supposed to identify the ordered pair and the quadrant that it is in. And there's a line here between ordered pair and quadrant in this table that just didn't print very well or scan very well in this document, so I had to just add that line in there a little bit more. So as we look at this ordered pair, we say this value of A is 3 to the left. So 1, 2, 3, which gives it an x value of -3, comma, the y value. Well, how high up is it? 1, 2, 3, 4. So it's -3, 4 is the ordered pair. And the quadrant it is in is quadrant 2. It's the top left one. As we move on to letter B, for example, we notice that this one is 2 to the right and 1, 2, 3 down. So that's +2, -3. So 2, -3. So once again, the first number tells you how far left and right you're going. Left is negative, right is positive. While the second number tells you how high up and down you're going. Down is negative and up is positive. So letter C then would be at 0, 2. It's 0 left and right, but it is 2 up. Whereas letter D, and I forgot to say the quadrants for B and C. So the quadrant for B is quadrant 4. Now you might be wondering, well, C, which quadrant it's in? It's between quadrant 1 and quadrant 2. And so it's not technically in a quadrant, it's between quadrants. And so what we'll list is that we'll just say that it is on the y-axis. And if it's on this y-axis, it can't be in a quadrant. Then letter D here will be the ordered pair 7, 1, which is quadrant 1. Point E will be the ordered pair -4, -6, which lands itself in quadrant 3. And our last pair here is point F, which is on the x-axis, and that's -5, 0, 5 to the left, 0 up or down. Once again, that's on the x-axis. It's between quadrants 2 and 3, but in neither. Now, a discrete graph would actually be like the graph we just have right up here above with these 6 points. And it is defined as a graph of distinct points. And for example, I guess I mentioned the one above would be an example, or I'll draw another one here. If I just have this graph here, and I start plotting some random points around. And these points could be literally anywhere, as long as my pencil wants to draw them. Whereas by contrast, a continuous graph is a graph with, W/ is shorthand for with, connected lines and curves. curves. So if this was my coordinate plane, a continuous graph could look something like this, to where instead of just being a bunch of points, it's almost like a connect the dots. Moving on, we'll talk now about what a relation is. And I need to rotate this page. My apologies on that. There we go. That's better. The definition of a relation is a set of ordered pairs. And it is important to note that the set of x values for these ordered pairs is called the domain, whereas the set of y values for the ordered pairs is called the range. And what we're going to do here is we're going to take these ordered pairs. So we have a set of ordered pairs on 1, 2, and 3, a different relation on 1, 2, and 3, and we're going to express them in a multitude of ways. So we're going to identify the domain and range. Then we're going to express it as a table, a mapping diagram, and a graph. And we're going to learn how to do each of these. Okay. So starting off here with the domain, we said the domain is a list of x values. Now I want us to note here that for both the domain and range, okay, this is important for us to add in here, that they are listed from, see, I'm trying to find a good place to write. I'll write up above here, okay? So domain and range are from least to greatest. I wrote too big. With no repeating. So you order the x values for the domain from least to greatest, no repeating, and the same thing's true with the y values for the range. So now let's identify the domain and range on number 1. So on number 1 here, the domain, which would be d colon, or the word domain colon, either one. I often do the d colon to abbreviate when I'm writing it out, unless it's already written there for me. Then we do this squiggly line, which is a brace, which we also see here, and that just tells us it's a set of numbers. So it's telling us, hey, a set of numbers is contained within this brace. And obviously your brace doesn't have to be perfect, mine sure isn't. And so I'm going to order the x values from least to greatest. So my smallest x value is -3 and there's 2 of them, but I only write it once. Then my next smallest x value is -2, then 1, and then 3. And so that's not the order necessarily I saw all of these in, because this -3 came last and first, but it's the order from least to greatest. And the range is the same idea, least to greatest of the y values. So the smallest y value I see is -4, followed by 0, 1, 2, and 5. And there's no worry about any repeating here, because they were all different or distinct y values. Now the table is also going to be least to greatest. But you do have repeats here. So I'll actually use all 5 of these boxes, but I'm going to emphasize the lines on that one there to make that a little bit more prominent. So as I list the x values here, the x values are least to greatest, but the y values aren't. So I should clarify. So the x values are least to greatest on a table, not the y values. The y values match the x values. So for example here, the first one would be -3, 1, followed by -3, 5. They both have the same x value, but we put the one with the smaller y value first. But as we look horizontally, we get an ordered pair. So the next x value I see is -2, and that is with the ordered pair 0, followed by 1, 2, and 3, 4. So as we look horizontally through a table, we see an ordered pair, and the x values go from least to greatest, with the y values going with their corresponding x value to make an ordered pair. And once again, we have a tie with x values, so they're the same number. You break the tie by looking at which y value is least to greatest as well. The mapping diagram. The mapping diagram is very similar to the domain and range, to where you have the x values listed in one place, the y values listed in the other, and it also is least to greatest with no repeating. So least to greatest with no repeating. So I'm going to do L to G, least to greatest. I'm going to put no repeating. And so when you list it, it's the exact same as the domain and range. So just a little bit ago, we said the domain was -3, -2, 1, and 3. And the range was -4, 0, 1, 2, 5, because once again, just like domain and range, it's least to greatest with no repeating. But now what we do is, like any map, you're trying to follow directions. And so we have to draw arrows here as we say, okay, what ordered pair is -3 a part of? Well, -3 is a part of an ordered pair with 1 as well as with 5. So I draw arrows so I can visually show that -3 goes to the y value, corresponds to the y value 1 as well as the y value of 5. Whereas -2 is with an ordered pair of 0 with the y value. 1 is part of an ordered pair with 2, and 3 is part of an ordered pair of 4. My apologies, -4. I miswrote that in the table there. There should be a -4 on that last y value of the table. I probably confused a few of us there, so I apologize for that. But I just went ahead and fixed that to make that a -4 for my last ordered pair on the table. And then now for graphing it, we just graph these 5 points. So as I graph these 5 points, I'll do like -3, 1, for example, -3, 5, -2, 0, and you could do these in any order. There's not any right order. 1, 2, and 3, -4. I typically just kind of go off of the table. Personally, I find that one the easiest for me to go from the table to the graph compared to the mapping graph or the ordered pairs of the graph. So that's what I do personally. Moving on, let's try the same exact thing with numbers 2 and 3. So number 2, go ahead and feel free to try and do as much of this as you feel comfortable with, and then pause the video, do that, and then come back and see how you did compared to me, or if you're stuck, look what I did. So number 2 here, the domain here, once again, D: or domain: either one. Least to greatest for the x values. We're listing all 5 x values here because there's no repeating, so it's -2, -1, 0, 2, and 5. The range, the same thing, least to greatest, no repeating, but there are no repeats, so we don't have to worry about that here. And it's -4, -3, -2, -1, and 4. Then as we make our table, we don't have to worry about any ties like we did before, but I am going to emphasize that line there. And then I'm going to write my x values from least to greatest with the y values going with their corresponding ordered pair. So since -2, -3 is part of an ordered pair, -3 goes next to -2, even though it's not the smallest y value. And so then next would be -1, 4, 0, -2, 2, -4, and 5, -1. And then the mapping diagram, once again, there's x on the left, y on the right, and you write it just like you did the domain and range, least to greatest, no repeating, -2, -1, 0, 2, and 5, whereas the range is going to be -4, -3, -2, -1, and 4. And then I start drawing arrows, so -2 goes to -3, -1 goes to 4, 0 goes to -2, 2 goes to -4, and 5 goes to -1. And the last one, at least, I go and graph these ordered pairs. So as I graph them, I have like -2, -3, -1, 4, 0, -2, 2, -4, and 5, -1. So I have these 5 ordered pairs. Moving on to our third example here. As we identify this relation, we notice, oh crap, there is none. Well, that's because it's over here on this graph. And so we have to take the graph and then write the ordered pairs, the table, the domain range, and the mapping from it. So I find it easiest to either go to the table first or the ordered pairs first. You pick. But really, you could go anywhere first. If you wanted to, you could do mapping first. But once again, I find the others to be the easiest. And then as you go through this, if you want to list it, and go ahead and do from listed as the least to greatest for the x values, since that's how we have the table anyway. And then everything else is least to greatest for both x values and y values. I can just work from left to right, knowing that my lower x values are going to be on the left and my bigger x values are going to be on the right. And so as I work from left to right and identify my ordered pairs, I'm going to list them here. I'm going to state -5 comma -4 is the first ordered pair, put a comma before the next ordered pair, and have -2 comma 3, 0 comma -3, 2 comma -5, and last but not least 4 comma 2. That's going to end my set of ordered pairs. And then I'm going to identify the domain and range. So the domain here, D colon or domain colon, would be -5, -2, 0, 2, and 4. Once again, don't have to worry about the repeating, but you do have to still put them least to greatest. And the range, same thing, R colon or range colon, -5, -4, -3, 2, and 3. And then the domain, once again, not the domain, the table, once again, the x values are least to greatest, and the y values go with their corresponding x values to complete the ordered pairs. But these are already actually listed least to greatest when I did my set of ordered pairs, just because I knew that would make my life easier if I did that. So I'm just going to copy down what I had from the ordered pairs in the exact same order since I already put it in this order. And then last but not least, the mapping diagram. And so the x values go least to greatest, and so do the y values, just like the domain and the range. And then we start drawing arrows to connect them. So for example here, -5 goes to -4, -2 goes to 3, 0 goes to -3, 2 goes to -5, and 4 goes to 2. Moving on to the next part. So once again, talking about domain and range, this time right now we're going to talk about domain and range for continuous graphs. So we just covered discrete graphs, aka when it's a bunch of points. What do we do when it's continuous, they're connected? So domain, it's a good idea to scan your pencil or kind of move your pencil or your mind or your finger or whatever left if it wants to write down what I'm writing here. It kind of wrote it down. We'll just rewrite that. Left to right. And the reason why I'm saying left to right is because you go least to greatest for the x values, and least to greatest is left to right. Range, scan your pencil, bottom, change that and to the word to, top, bottom to top, and identify the y values that are touching or on the graph. And the reason it's bottom top is, once again, we want the least to greatest for the y values, and the lowest y values are at the bottom, where the highest y values are at the top. Now, as we're supposed to identify the domain and range for these types are usually written using inequalities or in interval notation. Personally, I prefer interval notation, but I'm going to present both for anyone that wants to potentially use a different one than I do. That's perfectly fine to use something different than me, as long as it's still something I'm saying, hey, this is okay still, and I'm wanting to give you the choice to use either one. So on number 1 here, how far left does this go? Well, this arrow tells us it goes left forever and ever and ever. It never stops going left, okay? And as we continue to trace along the graph, left to right, I notice that it's everywhere is an x value. Everywhere is part of the graph. I'm touching the graph at every point. It's not like I picked up my pencil and was like, oh, stop. An example, if I were to pick up my pencil and stop, would have been like if there's like this, because then I would have like stopped here and then kept going here. That didn't happen at all. Let me undo that, and then it goes forever right as well. So this is going forever left, forever right, and so what we say here is this is the interval of -infinity to infinity. It's going everywhere, with both being parentheses because you can never reach infinity or negative infinity. Very similar to when we did inequalities back in chapter 3. You could also write this as a double-lined R, stating that's all real numbers, aka any x value, and every x value is part of this domain or graph eventually, if you take those arrows out forever. Now the range will be a little bit different here. That's the y values low to high, and as you might notice, not all the y values are part of this graph. For example, the lowest we ever get is right here, whereas it goes up, 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 up in each direction forever. That's what those arrows mean. Not only is it going left or right, it's also going up from each of those. And so we say, okay, from low to high, the lowest y value we ever get to is right here. That is a y value of -2. And it goes up forever, so that'd be to infinity. And so the y value of -2 is a closed circle. It's not like it's an open circle. And so it's a bracket, whereas infinity is a parenthesis, because infinity is always a parenthesis. Now, if you wanted to write an inequality for this, the inequality would be y is greater than or equal to -2, aka the y values for the range, not x, but y, since it's a range, are -2 and anything higher than that. Let's go and do a negative number 2 here. There's no arrows as far as this goes. It's just a circle. And so how far left to how far right do we go? So we go left to here, we go right to here, and it's everywhere in between. There's no breaks or gaps like I was talking about when I covered up the graph with the white earlier. And so the farthest left it goes is -3. And the farthest right it ever goes is +3, and it's everywhere between there, as we mentioned. And because it's a closed circle, it's not like an open circle. If it was an open circle, you would see it distinctly. It's a bracket. And the domain can also be listed as the compound inequality. -3 is less than x, which is less than or equal to 3. I said less than, but it's less than or equal to on each of those. Because x is between -3 and 3, but also including -3 and 3. The range, low to high, the lowest it ever gets is here, and the highest it ever gets is here, and it exists everywhere between, as we mentioned. And so the range would be -3 to 3 as well. Or you could also write it as -3 is less than or equal to y, which is less than or equal to 3. So because we're talking about the y values, we'll list y. I'm going to emphasize this line separating domain and range. And I'm going to do that on the others as well. So I'll have to do that on example 4, as well as example 6, and continuing from there. But let's go ahead and go to example 3 here and talk about the domain and range. So left forever, right forever, no breaks in the graph. And so that's -infinity, infinity, just like number 1 was. Or you could also list it as the double-lined R, which just means all real numbers. The range, down forever, up forever, and everywhere in between. So this is also -infinity to +infinity. It goes down forever and it goes up forever. Or, once again, that double-lined R. For the x values, it goes left forever, it goes right forever, everywhere between, no breaks or anything like that. So it's -infinity, infinity. That's going to be decently common here to see that, especially when there's arrows. And the domain is also listed as all real numbers. Once again, you pick between the two that are writing there, the purple and the light blue. I don't care. Once again, I personally like the purple more typically, but you do you, and pick your preference. The range, it goes down forever, but as we start going up, because we go least to greatest, so down to up, we notice that it stops going up right here at the y value of 5. And so the range will be -infinity to 5, because it's the highest y value it reaches, with -5 being, -infinity being a parenthesis, but 5 being a bracket, because it's not like an open circle or anything. Or you could also list it as y is less than or equal to 5. It's 5 and anything lower. Number 5 here, how far left to right we go. So there's no arrows. When it goes left to here, right to here. So that'd be the domain of -1, 5, with both being brackets. Or you could write it as a compound inequality. It'd be like an and inequality, like it was before. -1 is less than or equal to x, which is less than or equal to 5. The y values for the range are going to be similar as far as how we write it, but different numbers. So the lowest we ever get is -3. The highest we'd ever get is +3, and it's everywhere between, no breaks or gaps. So it's -3, 3, very similar to what we saw on number 2. Or -3 is less than or equal to y, which is less than or equal to 3. Number 6 here, these arrows tell us that it goes left and down forever, as well as right and up forever, with no breaks in the graph. Since it goes left forever and right forever, that's -infinity into infinity, or the all real numbers. And with it going down and up forever with no breaks in the graph, it's also -infinity, infinity for the range, also written as a double-lined R for all real numbers. Moving on here. Continuing to do more of these. So this one goes left forever, it goes right forever. So it's once again -infinity, infinity, or that double-lined R. The range, it does not go down forever, but it does go up forever. So even though those arrows are listed below where we see here, it still means it goes up higher. The lowest we ever get, since we have no down arrows, is right here. And so that would be the y value of -3. So it's -3 comma infinity, with -3 being a bracket because there's no open circles there. Or y is greater than or equal to -3. Oh, my all real numbers didn't finish there. That or I accidentally undid it. Here, the domain, the farthest left it goes is here, but it goes right forever with no breaks or gaps in between. So its x is greater than or equal to, if you're writing in the light blue way I've been doing it, x is greater than or equal to 1, that's -1. Or you could write it as -1 comma infinity, with -1 being a bracket because it gets to -1. It's not an open circle. The range, how low does it go? Forever. How high does it go? Forever, with no breaks or gaps. So that's -infinity comma infinity, or all real numbers. Number 9. This one's tricky. So the x values is actually just 1, and it only goes here. It's no other x values, never moving left and right. So one way you could write it is 2, with brackets on each side. There's no comma, and so we just say for the one number, 2 is included. It's not an open circle the whole way or anything like that. It'd be odd for it to be an open circle the whole line. Can't even happen actually. But anyway, regardless, we have this 2 that it reaches as part of it, so it's brackets on each side. You can't just do one side. Another way you could write it is x equals 2. Now, typically, like I mentioned, I typically write the purple one, except for a couple cases, and this is one of the scenarios. When it's just equal to one number like this, I typically write the blue. But once again, it's a matter of preference. The range, it goes down forever and up forever, though. So the range is pretty normal for what we've had so far, which is -infinity comma infinity, not an uncommon one to us by now, or the double line R. On number 10, it's kind of the opposite end of the spectrum. Instead of being a vertical line, it's a horizontal line. And this horizontal line goes left forever, and it goes right forever with everywhere in between. So the domain is -infinity, comma infinity, or those all real numbers. The range, however, is going to be much more like the domain was on number 9, where it's just that one number. It's never going up or down. It's just the y value of -4. So it'd be -4 in brackets with no commas or anything. It's not moving up or down. Or you could write it as the equation y equals -4, which once again, on a time like this, when it's just equal to a number, I just typically write it the equation like I do in the blue. Number 11 here, we experience an open circle for the first time. So from domain, left to right, the farthest left is here, the farthest right is here, but this is an open circle. Good to note. So the farthest left is -2, the farthest right is 5, but it's an open circle at 5, so it's a parenthesis at 5. Closed circle at -2, a bracket at 2. Also written as -2 is less than or equal to x, which is less than 5. Notice the one between x and 5 is less than, not less than or equal to, because it's an open circle. Now, in dealing with the range, we're talking about the low to the high. So the lowest point is here, and the highest point is here. So the lowest point is -2, the highest point is 1, -2 is an open circle, so it's a parentheses, 1 is not an open circle, so it's a bracket. You could also write it as -2 is less than, not less than or equal to, y, which is less than or equal to 1. Moving on to number 12. So notice that these are all closed circles, not open circles. Other than that, noting that there will be no parentheses, only brackets, the points don't really affect us as far as noting that they're points rather than just part of the graph a little more seamlessly. So the farthest left and right, the farthest left is here, farthest right is here. So that would be -4, 5, 4 to the left, 5 to the right, with both being brackets. Or we could write it as the compound inequality. -4 is less than or equal to x, which is less than or equal to 5. Range, same idea, but now we're doing the y value, so the low to high, bottom to top. The lowest we get is here, the highest we get is here. And so that would be the y values of -3 to 5, both being brackets. Or the compound inequality, -3 is less than or equal to y, which is less than or equal to 5. Let's move on to number 13. So we have an open circle, good to note. It goes left forever, but it stops going left stops going to the right here. So the farthest left is negative infinity, where the farthest right is 2. Open circle at 2, so it's parentheses, and infinity and negative infinity are always parentheses. Or the inequality, not compound inequality, x is less than 2. 2 are everywhere lower than 2, but not 2 itself. The range, we're going low to high. So the lowest is the bottom, and forever to negative infinity. But the highest it ever gets is the y value of 0. And that'd be a parenthesis for the same reasons we stated before for the domain. The range can be written as y is less than 0, not or equal to because it's an open circle, but it's 0 and anywhere lower. Number 14 here. As we go left to right, we notice there's a closed circle and it stops, but to the right there's an arrow and there's no breaks or gaps. So the domain is farthest left, -2, farthest right, infinity, with a bracket around -2. Otherwise written as x is greater than or equal to -2, because -2 and everywhere to the right of that. The range is low to high. So the lowest number we see is -4 for the y values, all the way up to infinity. And that, assuming that -4 would be a bracket. Or the inequality y is greater than or equal to -4. -4 and anywhere above it. Moving on, now we're going to talk about what functions are. So a function is a special relationship between values where each input, or x, has exactly one output, or y. So I'll list some ordered pairs here so we can see an example versus a non-example. So an example of a set of ordered pairs of relation that would be a function would be -3, 2, 5, -2, 6, 7, and 0, 7. And there's a million different things that could be functions and a million different things that could not be functions, but I'm just listing one of each here. So then a non-function would be like this, for example. -4, 1, -1, 7, -1, -2, and 5, 6. And we said that it's a special relationship where each input has exactly one output. Each x goes exactly to one y. A way we can think of functions is you put something in, you get something out. You put something in, you get something out. Just continually over and over again. Put something in, get something out. So for example, in this function, you put 3 in, -3 in, you get 2 out. You put 5 in, you get -2 out. You put 6 in, you get 7 out. You put 0 in, you get 7 out. And because none of the x's repeat, you don't have 6 going to 7 and 6 going to 5, for example. You only have 6 going to one thing. You only have 0 going to one thing. And even though 6 and 0 both go to 7, that's okay because that's 2 x values having one y value. But what we're concerned about is making sure that each x value only has one y value, which is the case. 6 has a y value, 0 has a y value. They happen to be the same. That's okay. What is not okay is over here where you have -1 going to 7 and -1 going to -2. So -1 goes to 2 different y values and the x's repeat. So when the x's repeat or you have an x going to multiple y values, it is not a function. But when the y's repeat or you have multiple x's going to the same y, that is still a function. A good way to think about functions is it's like a vending machine. And a good, proper vending machine, how it should work is that you figure out the item you want, you push the code, obviously you pay as well, but you push the code and you get the item out. And it's going to be consistent. Every time you're going to get that same item out. It's not like I'm going to come one day, I'm going to type in 5, and I'm going to get -2, which let's say it's a Butterfinger. And then the next, And the next day I say, oh, I'm going to push this button because I want a Three Musketeers. Or today I'm going to push this button because I want a Twix. Okay? That would be like a function. And if I wanted a Twix again that fourth day, I'm going to push this same button that I did the first time I wanted the Twix, and get the Twix out again. It's staying consistent that I'm putting the same thing in, I'm getting the same thing out. Whereas how a vending machine does not work, or what is not a function, is that I push this button one time, -1, and one day I get a Twix. And I'm like, awesome, I love Twix, okay? And the next day I push -1, but instead of a Twix, an Almond Joy pops out. And it's like, whoa, whoa, whoa. I put -1 in, I wanted the same number out. I pushed the same button because I wanted the same item. Why are you giving me a different item? I don't want Almond Joys, those belong in the trash after all. I just want the Twix. And so that would not be how a proper vending machine works, and very similarly, that is not how a function works either. So anytime that would happen, that's not a function. And now it is important to note that a function is still a type of relation. It's just a more specific type of relation. Just like a freshman is still a high schooler, it's just more specific than just saying a high schooler. So now determine whether the given relation is a function based on what we're seeing. So number one, as we look through all these ordered pairs, I'm keying in on the x values. I'm looking, okay, do I see any x value twice? Do I see any x value going to multiple y values? And as I look, I see 5 distinct x values, none of them repeating. And so I say, yes, this is a function. Whereas when I look at number 2, I look at the x values and I notice, I'm like, oh, 2 right here. I see 2 twice, and it goes to -4 and +4. -4 and +4 are 2 different numbers. And so because 2 goes to 2 different numbers, this is not a function. So I'm going to put no, and it didn't ask me for a reason why, but you might want to start listing reasons why when it's no. Hint, hint, wink, wink, nudge, nudge, cough, cough. And a reason could be that 2 repeats, or 2 goes to multiple y values, or 2 goes to -4 and to 4. Anything like that would work. Number 3 here. So is this one a function? Why don't you try number 3 and 4 on your own, and then play the video back after you try it. So number 3 here, we see -3 repeating. So no, it's not a function. That's because -3 repeats, or -3 goes to both -1 and 2, or -3 goes to 2 different y values. Whereas at number 4, we see all these x values be unique. We don't have any x values going to multiple y values. So yes, this is a function. Doing the same thing here, but now if we look at tables. So once again, these are x values, and we're looking to see, hey, do any of these x values repeat or go to multiple y values? And so why don't you go and try 5 through 10? Hopefully you tried those now, and we look at 3 and 3, and we're saying, oh, nope, not a function because 3 repeats, or 3 goes to both 5 and 3. Number 6, yes, this is a function. We don't have any x values repeating. We have a y value repeating, but that's fine. We're only concerned about the x values repeating. And I should rewrite my yes because that was pretty poor. Number 7, yes, this is a function. Once again, we don't care that we have y values repeating, even if we have multiples that are repeating. Number 8, though, is not a function, and the reason why is because this 4 repeats. It goes to -3 and 2, so I'm going to put 4 repeats. Number 9 is in fact a function, even though the y value is always the same, still a function. And number 10, also a function, even if it just goes in order of 1, 2, 3, 4, 5 for grins and giggles. Now 11 through 13 are the same thing, but on a mapping diagram, so go ahead and try these. Hopefully you tried these by now. As we look at these, we have to remember that each arrow signifies an ordered pair. So -3, 0, -1, 4, 2, 7, and 4, 4 are the ordered pairs. There's 4 of them here. And this is a function, even though we have both -1 and 4 going to 4. That's because, once again, we can have the 2 x's going to the same y value, but it's a concern when there's one x going to multiple y values. To bring it back to the vending machine example, that would be like, for example, on a problem like 11, where multiple x's go to the same y, that'd just be like a popular item having 2 different spots. So maybe Butterfingers are really popular in a particular vending machine. A lot of people get them, and so they're like, oh, we need a second spot for Butterfingers because we run out so fast. And so there's just 2 spots for Butterfingers, and you push one button, you get a Butterfinger. You push the other button, you also get a Butterfinger. That's perfectly fine. We do see that in vending machines. Now, as we turn our attention to number 12, this is not a function. And the reason why this is not a function is because -1 repeats. -1 goes to both -1 as well as to 7. So -1 repeats. It goes to two different y values. It's part of two ordered pairs, not a function. Number 13, though, is a function again, even though we have two x values going to the y value of 2. That's perfectly fine. Moving on to our last page for this notes. Lots of pages in this section today, is the vertical line test. The vertical line test is another way to tell if the relation is a function. This is a way to tell graphically or from a graph whether a relation is a function or not. And so the vertical line test states that if a vertical line, let me make my if a little bit less bad, if a vertical line intersects a graph more than once, then it is not a function. So if a vertical line intersects a graph more than once, it is not a function. If it intersects it once or less, it is a function. So let's do some examples here. So if I have a graph here of a function and a non-function, one that could pass the vertical line test is this purple graph. A vertical line, any vertical line I would draw, I'll just do them in dashed lines, would only ever hit 1 point. And even if this arrow eventually came over, it would hit multiple points. But if it hits more than 1, it's a concern. If it hits 1 or less, not a concern. And so here, for example, if I do not a function, I could do something like this. And this fails the vertical line test and is not a function because even though maybe right here at this one spot, it only hits 1 point. And over here, it never hits any points. But because there is at least one spot where I could draw a vertical line and hit more than 1 point, denoted by those two x's, this is no longer a function. It is not a function. It fails the vertical line test. So some examples using this vertical line test. So as we look through here, would any vertical line hit more than 1 point on the graph? And yes, right here, it hits more than 1 point. So no, this is not a function. And a potential explanation is that, once again, the x's repeat, -3 repeats, that's the x value here. Or you could say that it fails the vertical line test, which I abbreviate to VLT. Not confused with the popular sandwich with bacon, lettuce, and tomato, a BLT. Number 15. Let's figure out if this is a function or not, and go ahead and try 15 through 21 as well on your own. So 15 here, there's no vertical line that can be drawn that would ever hit more than 1 point. It would either hit 1 or none. So yes, this is a function and it passes the vertical line test. Number 16 also passes the vertical line test. No vertical line would ever hit more than one function. 17 is not a function. And the reason why is, even though once again it passes here, it fails other places where it hit more than 1 point on the graph, like here and here, for example, this vertical line. And so this fails the vertical line test, or you have x values repeating, however you want to word this. But I really like the fails VLT here. 18 is also not a function. It also fails the vertical line test. Because anywhere in the middle of the circle, or anywhere between the ends of the circle, anywhere between those two things, you have any vertical line here in the middle that you could possibly ever want to draw, would all hit more than 1 point. And so because even one of them were to hit more than 1 point is enough for us to tell us that it fails the vertical line test, and thus is not a function. Number 19, no vertical line would ever hit more than 1 point, and so this is in fact a function. Number 20, this might be tricky. Let's think about this. A vertical line would have hit more than 1 point. This vertical line is hitting a lot of points. It's hitting the entire line, as a matter of fact. And so because of that, this fails the vertical line test. And on 21, Any vertical line would only hit 1 point on this one. No vertical line ever hits more than 1 point, so this passes the vertical line test, and it is a function. And with that, we wrap up Algebra 1, Section 4.1.